Continuing with our exploration of calculus on polar curves, we're going to look at how we can find the area of a polar curve, or the area between two polar curves. And we're going to see that we will utilize some notions we've used before about approximating areas with familiar shapes. Recall that when we learned to find the area under a curve defined by a function y equals f of x, we utilized rectangles. We calculated the area of those rectangles and then let the number of rectangles go to infinity to discover that the area was exactly equal to the definite integral. Rectangles are inconvenient shapes in polar curves, but instead, for a polar curve like the one we see here, we can imagine sweeping out the area with a series of sectors. We know how to calculate the area of a sector, so we can see that if we sum up the area of all of these sectors, we'll get a good approximation for the area that we wish to find. We know from geometry that the area of a sector with angle theta in a circle of radius r is given by theta over 2 pi times the area of the circle, which is pi r squared, and that simplifies to be theta over 2 times r squared. If we've divided up our region into n sectors, then the angle for each of those is going to be delta theta sub k, and the radius of each is going to be r of theta sub k, where r equals f of theta is the polar curve that we're working with. We then know that the area of each of our sectors, a sub k, is going to be delta of theta sub k, the angle, divided by 2, times r of theta sub k, the radius, squared. If we add all of these up, then our area is approximately the sum from k equals 0 to n of a sub k. Once we're done with the geometry, we get to do some calculus, and we're going to define the area of our region that falls between the angles theta equals alpha and theta equals beta as the limit as n goes to infinity of the sum from k equals 0 to n of a sub k, the area of each of our sectors, which of course then becomes 1/2 the integral from alpha to beta of r of theta squared d theta. Let's go ahead and see if we can figure out the area of one petal of this rose we've been looking at. Its formula is r equals 2 cosine 2 theta. We can see that that petal is carved out for theta values between negative pi over 4 and pi over 4. So our area is going to equal 1/2 the integral from negative pi over 4 to pi over 4 of our radius squared, which is 2 cosine 2 theta, all squared, d theta. So that gives us 1/2 times the integral from negative pi over 4 to pi over 4 of 4 cosine squared of 2 theta, d theta. We'll move the 4 outside to get twice the integral from negative pi over 4 to pi over 4 of the cosine squared of 2 theta d theta. We know from our integration techniques that when we have a cosine squared, we're going to rewrite it using a power reducing formula. So we're going to write that as 1 plus the cosine of 4 theta all over 2 d theta. And so then when we take our antiderivative, we're going to get 2 times 1/2 of theta plus 1/8 the sine of 2 theta. Nope, the sine of 4 theta. And we're evaluating that from negative pi over 4 to pi over 4. That gives us 2 times, plugging in pi over 4, we get pi over 8, plus 1/8 the sine of pi, which is 0, minus 1/2 times negative pi over 4, which is negative pi over 8, plus 1/8 the sine of negative pi, which is still 0. Oops, I wrote theta instead of 0. There we go. And so we get 2 times pi over 8 plus pi over 8, which is pi over 4. So we get 2 times pi over 4, which is pi over 2. So the area of one petal of that rose is equal to pi over 2. And of course, if we wanted to do the whole thing, we could use its symmetry to say that the whole thing is 4 times pi over 2, or 2 pi. Let's try another example. This time, we're going to look for the area that is within the circle r equals 1, but lives outside the cardioid r equals 1 plus cosine theta. So we can use familiar ideas again from finding areas of curves where we can subtract the difference between these two areas here. What we're going to start off with is figuring out where these two curves intersect. So we have r equals 1 and r equals 1 plus the cosine of theta. Those are going to intersect where 1 is equal to 1 plus the cosine of theta, or where 0 is the cosine of theta. These curves are both carved out for 0 less than or equal to theta less than or equal to 2 pi. So theta is equal to 0 or cosine of theta is equal to 0 when theta is equal to pi over 2 or 3 pi over 2. So those gives us the limits of our integration. Those are our alpha and our beta. So we know that our area is going to be 1/2 the integral from pi over 2 to 3 pi over 2. But now we have to look at the curve. The circle's radius would be 1 squared inside the integral. The cardioid's radius would be 1 plus the cosine of theta squared. So if we take the difference of those two, we'll get the selected area that we're looking for. Now we just solve. So this is 1/2 the integral from pi over 2 to 3 pi over 2 of 1 minus 1 plus 2 cosine theta plus cosine squared theta, dtheta, which is 1/2 the integral from pi over 2 to 3 pi over 2 of negative 2 cosine theta minus cosine squared theta dtheta. So that's going to give us 1/2 the integral from pi over 2 to 3 pi over 2 to, whoops, I'm ready to take antiderivatives. Oh no, I'm going to rewrite the cosine squared first. So I have negative 2 cosine theta, and I'm again going to use a power reducing formula. So I'm going to get minus 1 plus the cosine of 2 theta over 2. And so if we just expand that all out and distribute that negative so that we're careful of our signs, we get negative 2 cosine theta minus 1/2 minus 1/2 the cosine of 2 theta, all with respect to theta. So we have 1/2 times the antiderivative of negative 2 cosine theta is going to be negative 2 sine theta. The antiderivative of negative 1/2 is negative 1/2 theta. And the antiderivative of negative 1/2 cosine 2 theta is going to be negative 1/4 the sine of 2 theta. And that's all going to be from pi over 2 to 3 pi over 2. Plugging in, we get negative 2 times the sine of 3 pi over 2 is negative 1 minus 1/2 times 3 pi over 2. And then we get minus 1/4 the sine of 3 pi, which is 0. Subtracting what we get when we plug in pi over 2, we get negative 2 times the sine of pi over 2, which is positive 1, minus 1/2 of pi over 2, minus 1/4 the sine of pi, which is again 0. Distributing and cleaning things up, we get 1/2 times 2 minus 3 pi over 2 plus 2. That should be a 3 pi over 4. We get plus 2 plus pi over 4, which is 1/2 times 4 minus pi over 2, which is 2 minus pi over 4. And that is our final answer. Okay, wrapping up what we know now about area of polar curves. If we're trying to find the area of some curve r equals f of theta, or r of theta, between the angles theta equals alpha and theta equals beta, we know that by using sectors to approximate and letting the number of sectors become infinite, the area is 1/2 the integral from alpha to beta of r of theta all squared d theta. If instead we want to find the area between two polar curves, where one of those curves is r equals f of theta and the other is r equals g of theta, then we can just use the formula a equals 1/2 the integral from alpha to beta of f of theta squared minus g of theta squared d theta.